I want to recap what we did in the magnetic fields unit. So we started with determining the shape and direction of a magnetic field using iron filings and a compass. And I just wanted to draw what we got again. So we found that a compass, if you would put it right over here, the compass needle would do something like this. The north pole of the compass, this side, would be repelled from the north pole of the magnet, and the south pole of the compass would be attracted to the north pole of the magnet, because likes repel and opposites attract. And so we found that wherever you look around this magnet, you would get a field that looks something like this. Because wherever you'd put the magnet, it would point along the field lines like this. There you go. That's a single magnet. When we are looking at two magnets together, then the field lines do some other things. So we have the same thing going on, that on a single magnet you would have these loops going from north to south, north to south. Same thing with over here, you'd get loops going from north to south, but the north pole of this magnet and the south pole of this magnet would also be interacting with each other. So the fields would kind of combine in the middle, and it looks like this. Now let's try it with the like poles together. So this is opposite poles together. Here's like poles together. So we'll have the same thing happening with the loops going from north to south on the individual magnets, but what happens in the middle is a little bit of a different interaction. Here's what it looks like. These magnets repel each other, and so their fields don't combine with each other in the middle. They kind of push each other to the side. So there's this empty space in the center where there is no magnetic field. They repel each other. The second part of the unit dealt with electromagnetism and right-hand rules. So we found that when current travels through a wire, or really anything, a magnetic field is created. And here's what it looks like when, let's say, the current is traveling upward through this wire. When the current travels upward, we use our right hand to figure out what direction is the magnetic field going to point. Because we remember, hopefully, that the field is going to create concentric circles around this wire. So I'm going to draw it down here. Something like that. Now, what we need to know is the direction of the field. Okay, so if you would put a compass in this field here somewhere, it would point a certain direction. And we use the right-hand rule to figure out what direction that is going to be. So, here's the current traveling upward. We use our right hand to figure out what direction the field is turning. So my thumb is the current, my fingers are the field, my fingers are going to be turning this way. Okay, so for me, if I was looking down at the top of my wire like this, it would be turning counterclockwise. So that looks like this. Here's just some arrows pointing in the direction of the magnetic field. So it's going to be turning counterclockwise like that, and so the compass would look like this over here, and if you put it over here, it would look like this. For the second wire, let's say that the current is actually traveling downward, like this. Now the field is going to look exactly the same. It's going to be these concentric circles, and the direction will just be the opposite direction, right? When you use your right-hand rule like this instead, you're going to find that the magnetic field turns in a clockwise direction instead of counterclockwise. But I want to draw this differently. So we used X's and dots to show direction when drawing a three-dimensional diagram is difficult. So we know that the field is going to be turning clockwise around here when you're viewing from the top. And so the field is going to be pointing into the page on the left side, and it's going to be pointing out of the page on the right side. Into the page is an X, like this, and out of the page is a dot. Okay, and that's because an arrow pointing at you, you would see a dot. You'd see the tip of the arrow first. An arrow pointing away from you, you'd see the back of it. You'd see the fletchings, and so that's why it's an X. Okay, and so this is just a different way to draw direction when we're talking about fields. So magnetic fields, we're drawing them on a two-dimensional piece of paper, but magnetic fields are a three-dimensional thing. And so in order to get around that three-dimensional drawings problem, we use X's and dots to say into the page and out of the page. Now for a coil of wire, which is going to be a more useful application of this type of thing, for a coil of wire, we're going to use a different right-hand rule. You could use exactly the same one. You could have your thumb pointing in the direction of the current. So my thumb is going to point clockwise like this, and your fingers would coil in the direction of the current, the direction of the magnetic field, that is, around the wire. And so if you used that rule, it would be like this, right? My thumb is pointing around the wire like that, and so my fingers should be coiling like this, which would mean that the field is pointing into the page in the center of the coil, and it's pointing around out of the page on the outside of the coil. But that rule is just sometimes difficult to do with your hand, and so in order to make it a little bit more convenient, we treat the curled thing, in this case the current, as your fingers, because your fingers are easier to curl. And so in the case of the one that you see in front of you, I'm going to curl my fingers clockwise, and my thumb is going to point in the direction of the magnetic field inside the loops. So that's pointing away from me or into the page. Okay, and so then we'll put some X's on the interior of the coil. It doesn't really matter how many X's you do, you're just showing that inside the loop, you have field pointing away from you, or into the page in this case. Okay, but remember that field lines are loops, and so where you have field lines pointing away from you here, you're going to have field lines pointing toward you on the other side. So you can imagine it like this. This field line is pointing away from you. It's going into the coil, and when it gets past, it loops back around and comes back at you this way. And so this is like one coil or one field line loop over here. And so the last thing that we're going to look at with right-hand rules and electromagnetism is a solenoid. So a solenoid is a coil of wire, or a set of coils of wire that have electricity running through them. And so each coil is doing what you just saw. Each coil is creating a magnetic field pointing, and in this case, it's all in the same direction. And so we can look at one coil of wire, this one right over here. This says that the current is pointing away from us on the top and toward us on the bottom. And so then we can use our fingers as the current. And so I would point my fingers away from me on the top and toward me on the bottom. So this is the direction that my current is running, and so my thumb points in the direction of the magnetic field in the middle of the solenoid, in the middle of all the loops of wire. Okay, and so in this case, we get a magnetic field pointing this way. Okay, but all the field lines are going to loop around like this, because magnetic field lines are loops. Okay, and there's going to be a lot of loops. I'm not going to draw them all, but there's more than just one. Okay, and that means that this solenoid has a north pole and a south pole. So the north pole is going to be this one, because magnetic field lines outside of a magnet point from north to south, or they point away from the north pole. Okay, so this is the north pole of our solenoid, and this is the south pole of our solenoid. And finally, we're going to revisit some magnetic force stuff. So here's one of the diagrams from your review. Use the diagram below to answer the following questions. Draw the magnetic field around the north and south poles of the magnet. Now that's not a completely clear request, but what it's asking you to do is, what does the magnetic field look like in this region over here? Horseshoe magnets have somewhat complicated magnetic fields, and so we're not asking for you to draw the whole magnetic field around a horseshoe magnet, just what's going on in this region over here. And we know that magnetic fields outside a magnet point from north to south, so something like this. Okay, we just really want to know what that magnetic field is so that we can use it to figure out the force on this wire. Okay, now we're going to use the force right hand rule, which looks like this. It's the flat hand rule. Okay, so your fingers are going to be the magnetic field, your thumb is the current, and your palm is the direction of the force. So right now, the force is coming out of my palm, pointing at you. Okay, now I'm going to adjust this so that it matches my diagram over here. My magnetic field is pointing down, so like this. My current is pointing at me, out of the page. So my thumb should be pointing at me. You can mirror me at your house. And so my palm is pointing to my right. Okay, that direction. So my force on this wire is going to be this way. Right or east? This question comes from your magnetic force assignment. Electrons flow west through a power line that runs along the equator in the Earth's magnetic field. What direction is the magnetic force on the power line? So in order to answer this question, you need to know what the direction of Earth's magnetic field is first. So if you remember, this is the Earth. The Earth's magnetic field points from north to south, from magnetic north to magnetic south. Now remember that magnetic north is down here and magnetic south is up here. And so Earth's magnetic field does this. Okay, and that means that if you're standing at the equator over here, here's you standing at the equator, the Earth's magnetic field is pointing north, past you. Yes, to magnetic south, but now we're talking about compass directions. So it's pointing northward. Okay, so that's important. The direction of the Earth's magnetic field is north. So the electrons are flowing west through this power line. Okay, but remember that conventional current, the current that we use for the right-hand rule, is the flow of positive charge. Okay, and so where electrons are flowing west, conventional current must then be flowing east. So then I is east. Okay, so this one's a little bit tricky for a couple different reasons. So now we're going to use our force right-hand rule. That's this one. So our current is pointing east. That's to my right. You can mirror me at home. and the Earth's magnetic field is pointing north. So I'm going to point north away from me that way. Okay, and that has my palm pointing upward. Okay, so the force on this power line is going to be pointing up. Okay, so what's the direction of the magnetic force? Up. If the wire is 100 kilometers long and Earth's magnetic field is 4 times 10 to the negative 5 Teslas, what current would be flowing through the wire if it was experiencing a magnetic force of 10,000 newtons? This is where we use our magnetic force formula. It's the first time that we have a calculation. So magnetic force on a current carrying wire is calculated using the field strength it's in times the current that's traveling through the wire times the length of wire that's actually in the field. Okay, and we need to remember that these things need to be at 90 degrees to each other. In this case, they are. We've got a north Earth magnetic field, we've got an east current, those are 90 degrees to each other, and we know that the direction of the magnetic force is up. So those three things are all 90 degrees to each other. We don't see any angles given to us in the question, and so we don't need to worry about that part of it. So we're solving for the current. Okay, so to get the current by itself, I need to divide by the field and divide by the length. So that gives me force divided by field and length is equal to the current. Okay, so that's 10,000 newtons divided by 4 times 10 to the negative 5 Teslas times 100 kilometers. But we don't want kilometers, right? It needs to be meters in this formula. And so 100 kilometers is 100,000 meters. Okay, so we're doing 10,000 newtons divided by 4 times 10 to the negative 5 Teslas times 100,000 meters. Now, if you're doing this on your calculator, either you need to divide them separately, or you need to put that whole thing in brackets there. And when you do that, you should get 2,500 amps. And we already know that's moving east. So finally, a magnetic force and angles question. This comes from your magnetic fields and angles homework assignment number 5. The current through a wire that is 80 centimeters long is 5 amps north. The wire is in a 0.3 Tesla, 55 degrees east of north magnetic field. What's the magnitude and direction of the force? Okay, so this 80 centimeters is in centimeters, and we need it to be in meters. So that ends up being 0.8 meters. Okay, 5 amps, that's all good. 0.3 Teslas, that's all good. And now there's this angle to deal with. So let's draw a diagram of what's going on here, and hopefully we can get a better idea of what kind of trigonometry we need to do here. So the current is flowing north. There is our current. The wire is in a 0.3 Tesla magnetic field, and that's 55 degrees east of north. Okay, so north is this way. 55 degrees east of north would be over here somewhere. So then we're going to draw the field like that. Okay, now we need the component of the field that is perpendicular to the current. Okay, so if we split this field vector into its north and east components, we're going to need the east component when we're doing this calculation. Okay, the north component runs along the current. That component of the field doesn't do anything. It doesn't exert any force. So the component that we need is this one. This is what we would call B perpendicular. Okay, this total field over here is B, and it's 0.3 Teslas. and this angle over here is 55 degrees east of north. And so the way that I've drawn it, that's 55 degrees. And so we're going to use sine to figure out what B perpendicular is. Opposite over hypotenuse. Now again, you can use the shortcut method, F equals BIL sine theta, as long as the angle that you're given is the angle between the current and the field. In this case it is, so you can feel free to just shorten it that way. But I'm going to do the whole version. So figuring out B perpendicular means that I need to use sine of 55 degrees equals opposite over hypotenuse, right? Sine is opposite over hypotenuse. The opposite side in this case is B perpendicular, and the hypotenuse is B. Okay, now I want to get B perpendicular by itself, so I just need to multiply by B, right? I've got it divided by B here, so when I multiply by B, it gets the B perpendicular by itself. So B perpendicular is equal to B times the sine of 55. Okay, and so we're doing 0.3 Teslas times the sine of 55 degrees. And that equals 0.246. 0.246 Teslas is B perpendicular. Now that's a rounded number. I'm not going to use this 0.246 in my final calculation. I'm actually going to use this thing here, 0.3 times the sine of 55. So when I'm calculating the force on the wire, I'm going FB is equal to BIL, or B perpendicular, which is the component that I'm going to use, times I times L. And so that gives me 0.3 Teslas times the sine of 55 degrees. That's B perpendicular. And then I'm going to multiply that by my current, which is 5 amps. And I'm going to multiply that by my length, which is 80 centimeters. But I don't want the centimeters thing, I want 0.8 meters. And when I multiply that out, I get 0.983 newtons. Okay, now if you're doing sig figs, look at the question. The current through a wire that is 80 centimeters long is 5.0 amps in a 0.3 Tesla field, and that's 55 degrees. 2 sig figs, 2 sig figs, 2 sig figs, 1 sig fig. And so if we're rounding this to sig figs, our final answer should be 1 Newton, right? Okay, I'm going to leave this here because I want you to see what the actual answer would be. Finally, we need to put a direction on this thing because this is a vector. Okay, now we need to use the right hand rule. So B perpendicular is our field, and that's in the east direction. The current is in the north direction, and so we're using our flat hand to figure out where the force is going to point. Okay, so my current is pointing north, away from me, that direction. My field is pointing east to my right. So this is going to be the easiest way to do it. And so my force is going to be pointing down. Okay, try it yourself at home. So that's our final answer. Again, if you're rounding it to sig figs, you end up with 1 Newton down.